So welcome students to video class 34, and we are going on to the next topic in this module, that is the Nyquist plot, or in your syllabus it is given as Nyquist stability criterion. Okay, so we'll be having one or two or three classes, so I'm calling this as part 1. Okay, so Nyquist stability criterion. Now, let me have a recap of all the stability analysis that we have done so far. We started with RH criterion and we made use of what? The characteristic equation, right? So using the characteristic equation, that's a mathematical approach. And not only that, that is called as an absolute stability. So it just gives you an answer whether the system is stable or not. Then we went on to study a graphical approach, which is the root locus, that again from the given characteristic equation. That's a graphical approach, and a time domain analysis. You can say that it will give you an idea about the time domain behavior of a system, because it gives you whether the system is a damped system, overdamped system, underdamped system. All those things can be analyzed from a root locus based on the value of the constant k, which is in the characteristic equation. Then we studied say we studied Bode plot. Okay, and Bode plot uses what? The open loop transfer function of a open loop transfer function of a closed loop system, and that too the sinusoidal open loop transfer function in Bode form, right? So from this we were able to analyze the system. This is called as a frequency domain analysis, because from this we get many of the frequency specifications like gain margin, phase margin, and so on. Okay, so this is another method by which, so this Nyquist stability criterion or Nyquist plot, it is also called as a Nyquist diagram. So this is another method by which you can ascertain the stability of a system. Okay, so as in Bode plot, Nyquist plot or Nyquist method also make use of the open loop transfer function of a closed loop system, that is, it is uh, it, so it actually starts with this g of s h of s. Now we have already found out the we already know this know the basics of this g of s h of s, or the generalized form of this g of s h of s, right? So that is of the form k into, okay, s plus s plus z1 into s plus z2, etc., up to divided by s raised to n into s plus p1 into s plus p2, or okay, etc. Okay, so you can say that this is a forward scale factor, and these are the terms associated with this open loop transfer function. Now basically you can call this as a function of s, right? So this is a function of s, and we know that this s is also a variable, and that too it is a complex variable. Okay, now this, in order to represent this s, we need two coordinates, right? You cannot represent this by a single coordinate. So if you want to represent a point s, you want to have minimum two coordinates, that is the real axis of s and the imaginary of s, right? Okay, so this is actually the so this results in what is called as an s-plane, right? Now we have a function, this, what is this f of s? This f of s is another function of this complex variable, Okay. Now, suppose you have an f of s. When you substitute this f of s into s, what happens is this can also be of the form. This becomes of the form some a plus jb, where a is going to be a function of s, right? While b is also going to be a function of s. So in order to plot this, in order to plot an f of s or a function which is a variable and that itself is a two-dimensional uh, variable, you need two graphs, right? One is to plot. One is already we have studied, that is the s-plane, and another one is the f of s. So if you want to plot this f of s, this f of s is actually, there also you can write like this, the real of f of s and the imaginary of f of s. Okay, that is, to plot this a and this b, you need another graph which is f of s, or a is the real part of f of s and imaginary part is of b is the imaginary part of f of s. Okay, so what are you actually plotting? You are actually plotting this f of s with respect to some of the points in the s plane. So in a sense, when you do that, you are actually mapping this s plane, mapping the s plane into another plane called as f of s. Okay, or you are trying to plot the s points, or it's a plane. So as I told you, s is not a single point, s is a complex point. So that means it will be having an imaginary real axis and an imaginary axis. Therefore that is a plane. So that is called as a point in the s plane. So we say that a point in the s plane is mapped into another plane f of s, and this is called as a mapping, while this function f of s is called as the mapping function. It is called as the mapping function. Okay, hope the things are clear up to this point. Okay, so in order to get the feeling of what I have just explained, I'm using an example. Say I am considering an S-plane. Okay, this is you are very familiar with. So this is the real of S-plane and this is the imaginary of S-plane, or you will call this a sigma or j omega. Okay, now consider you have a point on the left half of this is the S-plane. This is the positive part, this is the negative part. Consider on the left half of plane you have say 2 points. Okay, I have identified a say 4 closed points which are close to each other. So it starts with a, b, c, d, e and f. So these are the 6 points that I have identified and I have closed this corner. So this can be called as a closed path, or this can be called as a contour, right? Okay, a path. Okay, so what I'm going to do is, so this point a is at -1, this point is at -4. So I have identified some points in between -1 and -4, and I have closed that point so that this contour is can be named as a, b, c, d, e, f. So this is a contour I have identified in an S-plane. Okay. Now suppose you have a function. Suppose you have a function f of s is equal to s plus 5. So what I'm going to do is I want to map this. Okay, I want to transfer this to another plane f of s. So I have defined a function f of s and I want to plot this f of s, right? So we know that f of s is also, when you substitute s is equal to sigma plus j omega, f of s is also a complex plane with imaginary that will also be having a point corresponding to each s, right? So that will also be having an imaginary f of s and a real of f of s, right? So what will be this? So let us try to plot this minus 4. What is going to be the point corresponding to this minus 4 when you plot f of s? So this is minus 4 plus 5 becomes equal to 1, right? So let us call that point as, so let us call that point as d dash. This is d dash. So we have seen that this d has been mapped to 1 in this f of s, right? Now what will happen to a? Now what happens when s is equal to minus 1? So this I am telling you why this is at 1, because at s is equal to minus 4, f of s becomes equal to minus 4 plus 5, which is equal to 1. So now what about, so this is the result of mapping the point D in the S-plane. Now what if I map A? Now A means, when you map A means putting S is equal to minus 1. So what's going to be your f of s? F of s is going to be equal to 4. So that means this comes over here, right? Right? Okay. Now let me tell you that this point, let this point be j1 and minus j1. So what I'm going to do is I'm going to plot this point E. What is this plot point E? This is actually minus 4 plus j1. Now when you substitute this, when you find your f of s, what's going to be this? j1 minus 4 plus 5, that becomes 1 plus j1. So if you can plot over a j1 here, what happens to this e? E becomes e dash, right? E becomes e dash, right? And that becomes 1 plus j1. So this is e dash. So what we can see is when you put minus 1 plus j1, that is this point f. So this is the point E. Now when you plot this f, you can see that this corresponds to j1 plus 4, and similarly you can plot this c and b. C and also b will also be plotted in this way. So when you join these together, so this will be j2. You may do it by yourself. You can see that you will get a closed path like this, right? Okay, so look at this, a mapping in the you got a points in the S-plane, and what I did was, using this mapping function, I have mapped this to another plane f of s, right? So you will get a different result. So a contour is mapped and you got a different contour, okay, right? And this is what is called as a Nyquist diagram. Okay, the Nyquist diagram, or it is actually the mapping of the S-plane into another another plane, which is defined as or into another plane f of s, so that will result in a different contour or different shape. And in that contour, or in that Nyquist contour or Nyquist plot, we will apply this Nyquist stability criterion to ascertain the stability. And you don't have to worry about that, what it is. We'll come to that later. Anyway, the first step is how to map an S-plane to this f of s. That's what we need. Now, so we have seen so all the points that we consider in S-plane can be mapped to f of s by using that mapping function, right? Okay. Now let us see some of the terminologies that is associated with this Nyquist diagram. So we have seen a closed contour. One is a closed contour. You know what is a contour. Okay. Now a closed contour is in an S-plane is a continuous curve. It is a continuous curve. Okay, beginning and ending at the same point, beginning and ending at the same point. Okay, so that means, say, this can be called as this path, that is I'm calling this as a dash. Okay, this one is a dash, right? A dash, B dash, this will be C dash, this is D dash, E dash, and F dash. So this A dash, B dash, C dash, D dash, E dash, and F dash is said to be a closed contour, right? This is said to be a closed contour. And another terminology is an analytical function. And you might have studied in your maths course about the analytical function. That is, a function is said to be analytic. That is, your f of s is analytic, means f of s will be differentiable at every point on this. So you have f of s, the derivative of f of x exists on all these points. That's what is called as an analytical function. So this is for the just for namesake I've just mentioned. Okay, now the third is called as an enclosement. Okay, so enclosement, that is an important point. Enclosement and encirclement. Now this is what we have done in this example is we considered a closed path in the S-plane, right? And what we did is we mapped that into another plane f of s, right? So we got a different picture, or we got the exactly the same picture. It must be like this. Okay, so you may be getting the same shape. Okay, no problem. So you can I mean, you don't have to draw like this, because I think I have not scaled this. You can use the same scale, so you will be getting the same shape, but it is in the right half of this plane, right? The left point, what we see was a left point in the S plane is when we were mapped by S plus 5. What happened was that particular thing shifted to another point. That's all. And that results in an enclosement. So some of the points gets enclosed, right? Enclosed in this, right? So that is called as an enclosement, right? So so a prescribed, this is a prescribed contour in the S plane. When it is mapped, that results in another enclosement, and it encloses some points which lie on the right of that this f of s, and which may be having a point of interest, and that all you will understand when we go into this Nyquist stability criterion. You don't have to worry about that. Now the fourth one is a point is said to be, now suppose if I am considering a point, say a point here, say P. Now this is the point of interest I am interested with. Now what happens is when you consider this point is encircled by this contour, and that is called as an encirclement. Okay, right? So when this is encircled, this encirclement can be in both directions, can be in clockwise direction or anti-clockwise direction. Okay, now so far we have, what we have done is clockwise direction is taken as negative and anti-clockwise is positive. Here here we are following anti-clockwise as negative and clockwise as positive. There is nothing wrong in interchanging that, just because I'm simply following what I have found in the textbook. Okay, that's all. There is nothing wrong in even interchanging that. For the meantime, so you might be wondering, I mean, I mean, what is the meaning of this clockwise and anti-clockwise? Anyway, this circles. So this circles means say, suppose if this direction, this is A to A. So that means this particular thing has got a direction. So definitely when you map this contour will also be having a direction. It may be in the clockwise direction or anti-clockwise direction. Do remember this encirclement can be a positive or a negative depending on the direction. Okay, so these are the four terminologies that we come across this in this Nyquist diagram. Okay, okay. Now, so far you have you know an idea about what we. I'm just having a recap since it's a new topic. So we considered a function f of s, and we have a complex point. So what we did is we can plot this s in f of s. So that is basically what it results is we are mapping many of the points in the s plane to I of s, and with an example I have explained. This is how it becomes. So you're not going to get the exact graph as in the s plane when you map this to f of s. You are getting a different, and when you consider a closed path, you can also expect a closed path in the f of s as well, but at in a different direction or at a different area, or it can be even different shape. Okay, now from this we have found out some terminologies: closed contour, analytical function, enclosement, and encirclement. So when you map this will be enclosing some points, and there can be encirclements. Encirclements means it circles. Okay. Now the another point is the principle of argument, which actually is the basis of this Nyquist stability criterion. And what is this principle of argument means? Say, for any closed contour in the chosen closed contour in the S plane, if I mean when you say, for example, say something like this. Imagine that this is your S plane, and this is having a contour. I am specifying this contour or this direction. Now I want to map this only, this thing. All the points inside this closed contour I need to map into, see, what is called as into an f of s plane. That is the real of f of s and imaginary of f of s. So the principle of argument says that this will result in, say, another contour, right? This will result in another contour in when you map this. That's what we have seen here in this example. Now, this f of s, the nature of this f of s is, so be careful, this nature of f of s is what the principle of encirclement says, that this f of s will encircle the origin as many times as the difference between the number of poles, okay, number of poles and number of zeros of f of s. Okay, right? So f of s, we know that it is an open loop transfer function, and if you plot this, if you consider this S plane, a contour in the S plane, and if you use this mapping function f of s to map this, you will get a different contour in f of s. And the principle of argument says that this f of s will encircle its origin, right, as many times according to the difference between the number of poles and number of zeros. The difference between the number of poles and number of zeros. Okay, so you can define the number of encirclements. We are concerned with the number of encirclements will be equal to z minus p, where z is the right, where z is the number of poles and zeros, and p is the number of poles. Okay, so this is your encirclement equation. N is equal to z minus p, and this is what is called as the principle of argument, which is the basic thread of analyzing or the stability, Nyquist stability criterion. Okay, now you might be wondering that there is only one circlement, then what is the point in saying that? Say, I will just give you an example like this. Say, if I am getting a diagram like this, right? Okay, so how many encirclements will it have? So this is one encirclement, right? This is one encirclement. So I'm going to show it in the different ink. This is one encirclement. Okay, the next encirclement can be, what do you mean by encirclement? Encirclement is nothing but you start from a point and reach that point. It is just as the loop that we have studied in SFG, right? So similarly, there is another encirclement of through this path. This is also another. So how many encirclements at the origin? You have n is equal to 2. Okay, hope you understood what is the meaning of this encirclement. So it depends on the figure that you get after your mapping. Okay, right? Right. Now, using this principle of argument, then what is our primary concern? The primary concern is, I want to check whether for the stability, what I am expecting is, when I have a pole zero plot in the S-plane, that is in the real and imaginary, right from the beginning of RH criterion onwards, what we are checking is, we don't want any poles to reside on the left half of the S-plane. Okay, now if I am plotting this whole of this left half, this is a closed contour, right? The right half of the S-plane. Okay, if I want to plot, why this is a point of concern, because I just want to know about the stability. Now I also know that the stability is affected only by the poles that resides on the right half of the S-plane. Now what if I can plot the whole of this right half to the given function f of s? So you're going to get another contour as per this principle of argument, and that contour will be what? Will be encircling within the origin, and that depends on the number of poles and the number of, that depends on the difference of the number of poles and number of zeros. Okay, now based on that encirclement, based on the number of encirclements, you can find out what? Find out, or you can dictate something called as a Nyquist stability criterion. Okay, so this is it. Okay, so the number of encirclements will be as many times as the number of poles and zeros that are enclosed by this S contour, right? So it depends on the, okay, now what we want to check is whether there is any chance of, we want to map this whole thing to this f of s, any chance of this f of s going into the right half. So that can be dictated by the principle of argument. So it will be encircling as many times as the number of poles and zeros, or the difference of poles and zeros are enclosed by this S contour. Okay, now the origin of this is G. So what is this? This is actually f of s is nothing but it is a GSHS. Okay, now from the Ruth-Hurwitz criterion, what we checked was, we checked actually the any right half plane in 1 plus GSHS. Okay. Now, if this is GSHS, what will be the point of interest? So, when you select GSHS, this origin is the point of interest, or around the origin we calculate the number of encirclements. Now, what is the difference between 1 plus GSHS and a GSHS? So this is also another function, say call it as f of f dash of s. Okay. Now, if you know this GSHS, right? Now, if I have the plot of G of GSHS and know the encirclements, I can also calculate the number of encirclements that it makes at -1. What is the impact of -1? You are changing the origin from 0 to -1, or this point is -1 plus j0. So this same figure can be, it's not necessary always, it depends, can encircle this -1 plus j0. So this contour is giving an information about GSHS. So if you consider this point -1 plus j0, then this contour will give you an information of 1 plus GSHS. Because what we ultimately want is, we want to know we are concerned with the characteristic equation. We want to know the number of poles, okay, the number of roots. Okay, that's what is RH criterion states. How many poles? So what is the need of, why do we need to consider this GSHS? Because we want to know the closed loop stability. And what is a closed loop transfer function? It is 1 plus GSHS. For a unity negative feedback, it is and this is actually, when this is equated to 0, this is your characteristic equation. Or in a sense, these are the poles of a closed loop system, right? These are the poles of a closed loop system. Now what I'm going to get is, this is the encirclement. When you have a contour of this around this -1 plus 0, you will get an encirclement from the figure. So from the Nyquist diagram, you will get the value of n. And what is n? N is actually, that is from the principle of argument, we found out that this is n is equal to z minus, say, p. And I am using the term p plus. Why p plus? Because what I want to know is, I want to know whether this right half encloses any one of the poles or zeros of this GSHS. So that is only the point that makes instability. That is the point of concern. So that's it. So you will get the number of encirclements from the given mapping. So you don't have to worry how you will be mapping. I will be explaining how to map and all those things. Now from where will you get P plus? P plus is nothing but, it is the open loop holes, right? The open loop holes that you directly get from the question. So your G of s, H of s will be given, and say for example, say you have s plus 1 and s minus 2, something like this. Okay, 4 divided by s plus 1 into s minus 2. You know how many poles you have? You have open loop poles as s is equal to -1 and s is equal to plus 2. How many p plus? P plus, the p plus means it is a number of poles at the right half. So the number of poles at the right half is 1. So this is 1. So you will get from the question. This information you will get from the question. This information you will get from the plot. From that you will be able to understand what is Z plus. Now this will be giving you what? Since you are changed the reference point to -1 plus j0, okay, hope you understood the change of this origin. Now the origin is changed to -1 plus g0 because we are concerned about 1 plus GSHS is equal to 0. That is a characteristic equation. Now you will be getting Z plus. Okay, now, now let's see what is this Z. So from the argument criterion, we know n is equal to Z plus minus P plus. Okay, so I'll be explaining what is this. So this you will get from, the contour. Now you don't have to worry about that contour, how to develop that contour. That is the main theme of this session that I will be explaining you in the next session. Okay, now this P plus you will be getting from your given GSHS. Okay, so just find out the number of right of poles. So it can be P plus can be 0 or P plus can be 1 or whatever it is. So from this you can evaluate Z plus as N plus P plus, right? So using this expression you will get Z plus. Now what is the relevance of this Z plus? Now we know that this is the Z plus that we have derived from the and this encirclement is actually the encirclement around minus 1 plus J0. Okay, and this is what is called as the Nyquist criterion. That is to find out the number of encirclements around the minus 1 plus J0. Now why do we need to go for minus 1 plus J0? Because we are interested not in GSHs, we are interested in 1 plus GSHs, which is the same contour, but the origin gets shifted to minus 1 plus J0. Now the evaluation of the circlements around minus 1 plus J0 is what is actually called as a Nyquist stability criterion. We'll come to that anyway, and how to, using this expression you will be finding out Z plus. Now I will be telling you after making you understand what is this Z plus. Now what is basically this Z plus? Now this is, even though this is the denominator of this transfer function. Now this is again a function which can be represented as P of S to Q of S, right? Okay, so that itself it can be considered as a function of P of S to 0. Now what is actually, when you equate this P of S to 0, basically what you get is zeros or poles. When you equate denominator numerator, it is actually the zeros. So the zeros of this characteristic equation, now it is very important. What I am going to tell is a very important statement. This zeros of the characteristic equation is nothing but what it is. It is actually, when you consider this is the zeros, okay, or when you equate 1 plus GSHS equal to 0, what you are getting is P of S equal to 0. That's what you do. So you are evaluating the zeros of 1 plus GSHS in a sense. That is actually, since it is the denominator of the original transfer function, what you are doing is you are actually finding out the poles of the characteristic equation, the poles of the overall transfer function of the closed loop system. Okay, now what about this Z plus? So when you consider this as Z plus, you will say that this is the right half poles of the transfer function, and that is what we need. Okay, and this criterion is what is called as the Nyquist stability criterion. So you have this expression. So from, I again repeat, this you will get from the contour, this you will get from the question. Okay, so just to get the encirclements, and the number of encirclements depends on the difference of poles and zeros enclosed by this S-plane. That is what is called as a principle of argument. Using that, the Nyquist criterion says that using this expression you can find out the right of poles of a closed loop transfer function, which actually causes the instability of the system. Now if your answer is Z plus is equal to 0, so what you are aiming for? You are always aiming for this condition, right? Whenever you have this Z plus 0 is equal to 0, you can say that the system is a stable system, right? What's the meaning of this? So Z plus is equal to 0 means the zeros of this characteristic equation is 0, or in a sense you can say that the poles of the overall transfer function on the right half is 0. So that means that's the condition for the system stability. Hope you understood this, and we'll do exercise in the next session.